Hi, I've got another multifunctional scope meter to review today, and this one was sent in directly from FNIRSI, and it is their 2C23T, which combines a dual-channel 10 MHz bandwidth oscilloscope, a 10,000 counts digital multimeter, and a 2 MHz function generator, all in this small device. On this channel, I have reviewed at least 10 handheld oscilloscopes right now, and in terms of 3-in-1 devices, this one is probably one of the smallest I have reviewed so far. For size comparison, you can see here is a Zotac ZT702S, and it is comparable in size, width and lengthwise, but the FNIRSI is quite a bit thinner compared to the 702S. Now, the MDS9208 I reviewed a while back, I guess, is a little bit smaller, and it also has similar bandwidth compared to the 2C23T, but it only has a single channel, and also does not have a dedicated oscilloscope input. And here I have the old one HDS 272S. For comparison, you can just see how much bigger it is compared to the 2C23T. Also, the FNIRSI feels very light compared to the other handheld oscilloscopes. Now, we'll definitely have to open it up later and see what the construction is like inside. Before I forget, the product link is in the video description below for those who are interested in getting one after watching this video. Since the 2C23T only has a 10 MHz bandwidth oscilloscope, and the scope only has a sampling rate of 50 meg samples per second, which is very modest. It is clearly geared towards the entry-level market. The reason I have the ZT702S out here for comparison is because it also has a 10 MHz oscilloscope and has a built-in 10,000 counts multimeter, but the ZT702S only has a single oscilloscope channel and does not have a function generator built in. So for an entry-level multifunctional device like this, there are actually not many out there that offer similar features. So from that perspective, the FNIRSI 2C23T is definitely quite unique. Now, maybe that is the strategy these low-end test equipment makers use, trying to squeeze in as much as they can functionality-wise for a given budget. Now let's take a look at some of the accessories in the product box here. Besides the manual here, you get a pair of these 6100 oscilloscope probes. Now I have quite a few of these already. These are 100 MHz probes, which should be plenty for the 10 MHz oscilloscope. You also get these DMM probes. Let's take a look here. These are actually very soft. Let's take a look at the tips. Oh, look at that. I actually like these. These look like gold-plated here, and they are very sharp, very nice. These are actually pretty much the same type of leads provided with the Zotac scope meters. I really like that. And let's take a look at what else. Of course, because we have a built-in function generator, you also get this BNC to elevator clips. And there's a ubiquitous USB-C cable for you to connect the device to the computer. And that's pretty much all there is in the box here. The 2C23T actually looks pretty appealing, of course. Looks are only skin deep. Let's actually power it on and take a deeper look. But of course, first we need to remove the screen protector here. I probably should have left the screen protector on. As you can see, it's a little bit reflective. Now let me adjust the camera angle a little bit. Alright, let's power it on. Looks like it boots up pretty quickly. Now, by the look of it, it boots into this menu where you can select which mode you want it to boot up into. You can see here, you can select oscilloscope, configuration, multimeter, and signal generator. For those who wanted the default mode to be multimeter or function generator, or oscilloscope for that matter, you can actually do that through the configuration. Let's actually do that first, because I also don't like the beeping sound, it's a little bit too loud. So let me change the config here. So you can see, not sure how clear it shows up on camera, let me zoom it in a bit more. So we have the language here, we have volume, and this is when I want to change it down. Let's go to, let's leave it to 10%. Auto shutdown, we turn it off, good. Screen brightness, this is already 100%. Default, the default setting is where you set the default to boot into. Right now it's off, that's why it's showing you that selection when we first boot up. But you can change it to whatever device you want to boot into. So let's say we want to do a oscilloscope. And let's see about. Now here's the version. You can see that the hardware version is only 0.4. Typically for a production device, you want the version to be above 1.0. That's just convention. But that said, I'm not sure what convention they're following here, and that probably doesn't matter that much. Okay, so now let's power it off and power it on again to see if the default is oscilloscope mode now. Yep, you can see now we're entering the oscilloscope mode. And you can see by default, both channels are enabled, of course. You can use the dedicated menu keys to select each channel and configure that accordingly. So let's actually turn off the channel 2. So first I press channel 2, you can see that, so now channel 2 is selected. So let's press it again, and you can see now the channel 2 is on, so we can use the arrow keys to turn it off. Of course, you can also change the probe settings and coupling here as well. So now channel 2 is off. Let's actually see if it remembers the setting when we boot it up again, because some scopes don't remember the setting, which can be very annoying. So let's power it off. Oh, by the way, the power button here, you cannot long press. If you long press, for example, like this, nothing is happening. So to turn it off, you actually just need to short press it, which is a little bit unusual because typically you want a long press to take effect. Anyway, that's just something to pay attention to. Let's turn it back on again. Yep, indeed, we only have one channel now. So far, so good. The operation is actually quite intuitive. Now, what is not intuitive is that almost every single button here on this 2C23T has dual purposes. By short pressing, you get one behavior, and by long pressing, you get another behavior. Unfortunately, the functionality of the long press is not labeled here, so you will have to refer to the manual, or you can simply explore, and you will eventually figure it out. For example, the trigger button here, if you short press it, obviously it brings up the trigger menu, but if you long press it, you can see that it moves to the multimeter mode. And of course, we'll take a look at the multimeter a little bit later. And by long pressing the cursor button, you can see we get into the signal generator mode. And by long pressing the move button, you see that we're back into the oscilloscope mode. Let me connect it to a signal source, and we'll continue exploring the oscilloscope mode. Oh, I want to show you something here. You can see that the BNC connectors here are flush with the case, and you have very little room around each of the connectors. So if you plug in a standard BNC cable, you can see you barely have enough space. Not a problem, just something to point out here. Anyway, so now we have connected to a signal source. Let's see if we can use a stand here. Yep, the stand works quite well. So now let me enable the channel output. You can see right now we're outputting a 1 kHz signal. Of course, we haven't acquired the signal yet. So let me try to acquire that. It's interesting that you see some artifacts while you are doing auto acquisition here, so let's try it again. Yeah, no problem. But one thing you notice immediately is that we're currently in channel 1, and by convention it should be yellow, but of course the trace is cyan, so that's really the opposite of what the convention is. For example, if you look at channel 2 here, that is kind of orangey-ish, and that should be the color of channel 1, but it's not standard. Anyway, I'm not sure why they can't follow the convention. Now let's briefly take a look at the operation of the oscilloscope here. So if I press the up and down button, so if I press up, it will reduce the attenuation, and press the down button, it will increase the attenuation, which is very intuitive. And the left and right button, of course, is to change your time base. So far, so good. The only thing that is a little bit confusing is this cursor button. It's not actually what you think. The cursor button is really for you to control the trigger level. You can see that when I press it, the trigger is highlighted here, and I can move the trigger up and down. So for example, not sure how easy you can see that. There's a pink arrow here. That's the trigger. So that's what this cursor button is. I had thought that the cursor is actually for you to do some kind of measurements, but unfortunately the 2C23T does not offer cursor measurement capability, which I don't really mind, as this is just a rudimentary 10 MHz scope. So as long as it can reasonably display waveforms, I think there really isn't too much I can ask for. Of course, to make sense of the waveform you're looking at, you will also need to turn on the parameters, otherwise you won't see the timing and other characteristics of the waveform. So let's do that. So you can see that you can press this button and you can go select the different parameters you want to add on to the display here. Let's just actually keep the default here. So let's see. And I think I need to long press maybe. Yeah. So you can see we are now displaying what we had selected, which is very good. You can see that the peak to peak is roughly 1 volt. That's what we set it at. And the frequency is 1 kilohertz right here. Now, I would have probably chosen the RMS as default instead of the average. So let's do that. So let's come here and select RMS, and let's deselect the average, and let's get back here. So now that is actually a little bit more useful. While we're at it, let's actually take a look at a few more waveforms. So this is the sinusoidal at 1 kilohertz. Let's take a look at square wave. And you can see that we do have some trigger instability here. As you can see, even at this low frequency, there's definitely some jitter in the waveform, which is actually not from the signal generator. So it's definitely the scope itself. Let's try ramp. No problem. Let's try an arbitrary waveform here. Yeah, you can see we are able to display waveforms at least at this low frequency with no problem. Let me try a few more. So here I'm trying to display an amplitude modulated signal. The carrier frequency is 1 MHz and the modulation frequency is 1 kHz. Now that's quite a modest AM signal, but we are struggling. Actually, we're not able to display that signal. You can see, and the only part you can kind of see that's an AM signal is, let me just stop this waveform here, and you may be able to catch that modulation envelope here, but that's about it. So let me actually change the frequency here on the oscilloscope to see if we can see it a little bit better. Let's reduce the frequency a little bit to, whoa, now we're starting getting all these artifacts. Let's do 100 kilohertz. And yeah, okay. So I think it is capable of displaying AM signal, as you can see right now. It's just not at 1 MHz. So for lower frequency signals, I don't think you have any problems, but definitely is struggling to capture that 1 MHz amplitude modulated signal earlier. And this is the same carrier frequency 100 kHz, except this time the modulation is FM, and the modulation frequency is 1 kHz with a frequency deviation of 10 kHz. And you can see that we captured the signal reasonably well, and the update rate is actually pretty decent. So now I have dialed up the carrier frequency at 1 MHz now, and you can see the FM signal, we can still capture it. But I don't think it's capturing that accurately here, because if you, for example, lower the frequency here, you can see that the modulation is a little bit off. Right now, remember, we're still having that 1 kHz modulation, so this definitely doesn't look the same as before, but we are able to display it. But if you further increase the time base, you can see that now we started getting some artifacts, which unfortunately is not part of the signal, but you are seeing these kind of weird waveforms. And I had turned off the modulation. Right now the carrier frequency is still at 1 MHz. And you can see we had some kind of quantization steps here. Not sure how much resolution we have on the DAC, but you can clearly see these are the quantization errors. Anyway, so as you can see, the scope is really rudimentary. And of course, given the price of the unit and given the market positioning, I suppose it serves its purpose as a very basic dual channel scope here. Now let's take a look at the bandwidth here. So for that, let me auto-acquire the signal. And right now we're at 1 MHz. It looks like it's struggling to acquire the signal. Let's try again. No, it's not able to acquire that signal. Let's actually reduce the frequency. That's interesting. So let's do 500 kilohertz. And let's try again. No, still can't. Let's go back to 100 kilohertz. So we can do with 100 kilohertz, but we're having trouble doing a 1 megahertz. Okay, so we're not able to acquire at higher frequencies. And let's manually adjust. So we're at 1 megahertz right now. You can see there is no issue. Let me change the trigger a little bit. So now, this is our 1 megahertz signal. Let's keep increasing the frequency to see what we get. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that looks like it is able to handle, at least from a sinusoidal perspective, a 10 MHz signal. And let's increase a little bit more, 11. Looks like the frequency counter is still able to sort of catch up, but let's see here. Yeah, but the captured waveform you can see definitely has some issue here. Right now it's 11 MHz, 12, 13, 14, 15. The signal becomes really wobbly here. 16, 17, yeah. So definitely you are really pushing it. So let's take a look at 15. If we zoom out, you will see that definitely this is already beyond the 10 MHz bandwidth, because you can see we are seeing some interesting artifacts here. And of course, the front end can handle the 10 MHz with no problem. As we can see, we don't have much attenuation of the signal here. Let me put on both channels to see what the situation is like. And now you can see that both channels are now having a 10 MHz input. The channel 2 is not very stable, but you can see there's no additional attenuation by introducing channel 2. You can see now I have it off, I have it back on. The attenuation is similar. Of course, if we reduce the frequency, we would get a more stable signal. For example, if I change it to, let's say we change it to 1 MHz, and we change channel 1 to also 1 MHz, and we require a signal here. The attenuation somehow is different for the channels, even though the signal is identical, but you can see we are actually able to capture the signal in a more stable fashion. So can we use this scope to observe a 10 MHz signal? The answer is, well, it depends. If you have a simple signal like a sinusoidal or a square wave, the answer is yes, you can, but you have to be aware that if you have any type of modulation, the scope may not be able to pick up the details. Now let's take a look at the built-in digital multimeter. It has 10,000 counts. It appears by default the multimeter goes into this automatic measurement mode. Now I think I had mentioned this before. Personally, I don't like the auto mode, as in some scenarios, the automatic switching does not really set it to the correct measurement mode. Anyway, you can always switch to the desired measurement by hand by these buttons up here. You can see that. The secondary functions are printed on the meter itself, but it is a little bit hard to see here. Also, I don't particularly like the bar graphs on both sides here. They are not particularly useful as they take up a lot of space, and usually this type of bar graphs don't update any faster than the digits here. Now, especially on these cheap meters. Actually, you know what? Let's actually test that. Now I have hooked it up with a bench power supply that is adjustable. So let me adjust the output and we'll see. And you can see that the bar graph doesn't really update that fast at all. Yeah, so you can see that bar graph essentially updates at the same speed as the digits here, which kind of defeated the purpose of having the bar graphs here at first place. In my opinion, they should have just do it without bar graph, or having it on top here so you can at least make the digits larger. Anyway, some people might like the funky look of it, I guess. Alright, now let's take a look at the DC measurement accuracy with my EDC NV216A voltage standard. So let me increment the output 1 volt at a time. 1, 2, 3, 4. The update rate is okay, but you can see that the accuracy is not that great. 6, 7, 8, 9, 10. Of course, because it's a 10,000 counts meter, you can see that now we're losing 1 digit here. I suppose, even with this display, is still within the spec. You can see that the accuracy is, for DC measurement, is 0.5%. Now let's briefly take a look at the AC measurement here. For that, I have hooked up the Unity UT61E Plus as a comparison here. So let me increment the variac output. And you can see that update rate on the 2C23T is roughly at probably 2 to 3 times per second, which is adequate but not as fast, obviously, as the 61E Plus. But nevertheless, you can see we are measuring roughly the same voltage here. And obviously the accuracy on this FNIRSI is specified at 1.5% for AC measurement. So give or take, that number is probably not that far off. Now let's take a look at resistance here. So let's zero out the meter. Wow, that's pretty fast. That's not something I was expecting. You can see that the measurement speed in resistance mode is actually really fast. That definitely sets this meter apart from some of the other meters that I have reviewed. So let's take a look at a resistor here. Now we have a precision resistor, 100 ohm. Yeah, you can see we're a little bit off, but I'm sure this is within the spec, maybe just barely. But nevertheless, we're measuring 100.7, of course. Now you can see that we zeroed out the meter already, and there's really no residual reading here. So it's just the measurement is a little bit off here. Okay, 100.5.6, that's the measurement result, but the speed is definitely pretty fast. Alright, moving on to the diode and the continuity mode. And let's first check out the continuity. The measurement is definitely latched. It's just not as fast as it can be, but it is definitely adequate. For the diode, let's go straight to the white LED, because not all meters can measure that. Let's take a look to see if this meter can measure a white LED. So, let's see. Yep, you can see we not only can measure it, but also it lights up, which means the output voltage is definitely above 2.6, as you can see here. Very good. Moving on to the capacitance measurement. And you can see we have some residual here. Can we clear it off? Let's see. Yeah, you can see we can clear out the residual, but not sure why it's taking so long. Okay, so we cleared it out. Let me test to see if we can measure this 22 picofarads capacitor here. And we might be able to. As you can see, we do have the resolution here. Yeah, it's quite a bit off, but, well, I suppose the reason it's off is because we have these long leads. But you can see, at least, we are able to measure the 22 picofarads, and if you subtract the offset here, and you roughly get 22 picofarads. So let me actually redo the measurement. Yep, that shouldn't be a problem. Very good. So now let's take a look to see if we can measure a larger capacitor here. This one is a 15,000 microfarads capacitor. So let's do that. And it probably will take some time, which is okay. Yep, as you can see, we have no problem measuring that capacitor. And by the look of it, we also have the ability to measure temperature. Let's give that a go. And it's showing 34 degrees right now, and let's see what is that in Fahrenheit. It's 93. Whoa, that's quite toasty. I suppose that's because it's measuring the internal temperature here. Let me find a thermocouple. We can see if we can measure the outside temperature here. And you can see that we can actually put in a thermocouple here. Here's the thermocouple. Wait, I just realized something. The spacing of the socket is actually not standard. You can see here the thermocouple, this is a standard spacing. And if I show you a standard multimeter, you can see that this actually plugs in any of these two slots with no problem, but not on this FNIRSI here. I certainly was not expecting that. Well, this is really a head scratcher, as multimeter socket spacing should be industry standard. Even the cheapest multimeter followed this standard. I don't know why FNIRSI feels the need to change that. Anyway, with that said, I doubt any of the entry-level users would ever notice this, but for something so fundamental like this, I would have just left it alone. Anyway, let me put in a different thermocouple probe. And let's see here. Yeah, you can see we are able to measure the temperature as I'm holding this, so that's good. The next test is this live wire detection. So for that, I'm actually going to let's actually change it to that mode. And I'm going to insert the probe leads. And let's give it a go. Yep, that actually worked out quite well. You can see I can test the live wire. And this feature is actually very useful, in my opinion. Now let's take a look at the current measurement side. For the current measurement, you have two modes, the low current mode and the high current mode. Currently, we're in low current mode. You can see we do have some offset here. Not entirely sure why. That's probably because of power supply. Anyway, so yeah, I unplugged it. You can see the reading drop down, but we still have that minus 6 microamps offset. But that said, it's not really a problem here. Now, we only have a resolution of 1 microamp in the low current measurement range. Most dedicated multimeters, 10,000 counts and above, have at least 0.1 microamp resolution. But for this kind of multifunctional devices, this is typical. Now let me enable the output. And you can see we're measuring 100 milliamps, no problem. Let me actually change it to amp range because I know on some meters the display would not be accurate if you mismatch the range and the input socket here. So let's do that. Okay, so that's actually no problem. So that's good. So now let's switch to the high current measurement. And we are not getting any reading correctly here. That is actually odd. I'm not sure why it didn't work before. Let me try it again. Let's move it back. Whoa! As you can see, we set it to amp, and now we're actually in the milliamp socket. You can see the measurement result is definitely not correct. Let's change it to low. So for some reason we didn't see that. So that's actually interesting. Anyway, let me change it to the amp measurement. Let's do that. And let's plug it in. So I think we need to cycle it. Yep. You can see we're now reading essentially 100 milliamps. So I'm not sure what that mechanism is. You can see if I press the reading again, and the first time I'm not getting a correct reading, but the second time around I'm getting the correct 100 milliamp reading. So not entirely sure what's going on. Let's try a 1 amp. And we're able to measure that with no problem. Now moving on to the function generator, you can see it is rather rudimentary as you only have sine wave, square wave, triangular wave, half rectified and fully rectified waveform here, and of course you have noise and the DC voltage. So those are relatively rudimentary. One thing I can see already is that output is not AC, it's DC. You can see we are starting from 0 up to the voltage specified here. So you need to be careful if you are outputting this to a device that is only expecting AC input signal. The output frequency does go up to 2 MHz as you can set it here. So let's try that. So let's give it 1, 2, that's the highest frequency. Let's try to auto-acquire that signal. Yeah, as you can see, we can output that with no problem. And let's see if we can output square wave at that frequency. Yeah, we can. And of course, you can also change the duty cycle of the square wave here. And by the way, the middle button here, you can turn it on and off. Let's actually change the frequency down a little bit here. 500 kilohertz. And let's change the duty cycle. Yeah, that's not a problem. So although it is pretty rudimentary as you can see here, the good news is that the output amplitude is continuously adjustable. In some implementations on these cheap multifunctional devices, the output levels can only be set to discrete values. So this is arguably much more useful. But the output amplitude only goes up to 3.3 volts. Alright, I just opened it up. Before we do anything else, let's actually take a look at the current consumption here. So let's power it on. We're drawing just under 500 milliamps. And let's change the mode here. It does not appear we're changing much. In fact, right now we're in multimeter mode. You can see we're still drawing about 450 milliamps. So let's go back to oscilloscope mode. Yeah, so the oscilloscope mode probably draws the least amount, but it's only by 10 milliamps, it looks like. So anyway, so we're drawing between 400 and 450 milliamps, and that combined with a battery of 3000 milliamp hours, you get a runtime about roughly 7 hours. And here is a view of the circuit board. By the way, there were a few screws in the middle when I opened up the case, and those were unusually long, as you can see here. These are the screws in the middle here, whereas on the side, the screws were just the standard screws here, you can see. But having 6 screws instead of just 4 in the corners here definitely adds the overall rigidity of the construction, so no issues here. I also had removed the input section shielding can, but before we do further analysis, let me actually flip it over so we can take a look at the reverse side of the circuit board here. Well, as you can see, there's not a whole lot going on the back here. We only have a few components here, and that is on the side of the digital signal generator here. So presumably, these components are part of the signal generator circuitry. Beyond those components, not too much going on this side. So let me flip it over, and we can take a look on the main component side. The input section is fairly basic, as you'd expect on a 10 MHz bandwidth budget combo device. We have a couple of these GS8094 quad-channel 350 MHz bandwidth op-amps, which is adequate for the 10 MHz front end. And that also explained why we didn't see much input signal attenuation above 10 MHz, because these op-amps have fairly wide bandwidth. And of course, we'd expected to see these 74HC4051Ds. These are 8-channel multiplexer demultiplexer chips. Also, you can see for each of the input channels, we have a solid-state relay and a trimmer cap. Now, the trimmer cap, you can see that the position of each one is actually exactly the same. So this means that they are probably just default settings, and there's not much trimming going on. That also means that by design, there's probably not too much variation based on the default components values. And up here in the middle, we have a couple of these 3P8-1030 chips. These are the input analog to digital converters. They are spec'd as 10 bits, 50 megasamples per second ADCs, and because we have 2 of them, they are fully independent between the 2 input channels. So from a hardware perspective, it definitely meets the spec'd 50 megasamples per second sampling rate. And the smaller chip between these 2 ADCs, that would be our FPGA. By the marking here, it is a GoWin branded chip. And according to the datasheet, the UV2 means it has 2304 logical units. You can see the trace length matching here on the PCB. This larger chip here, of course, that's our MCU, and it is a 32F403. It is made by Arduino, and it has a 32-bit ARM Cortex M4 core. On the digital multimeter side, you can see, unfortunately, the chip number has been etched off. I was hoping we could figure out what they're using here, as the multimeter performance is quite good. Oh well. You will notice that besides this what appears to be a PDC resistor at the input here, we don't have much additional protection. And by the way, this 6-pin device here seems to be a VPT DC to DC converter. Towards the bottom here, we also have a programming header. By the look of it, of course, we have another one on the top of here. Presumably, the programming header on the top is for the FPGA, and this one at the bottom here is for the MCU. And looking at this side, it doesn't seem like we have any dedicated hardware for the signal generator. You can see this is the signal generator output BNC. The only circuitry we have is in this area. And besides, by the look of it, a few op-amps and whatnot, we don't really have anything else. So presumably, the signals are synthesized by the onboard MCU. And this section would be the output for the signal generator. And the chip towards the right of the USB port is a 4056A, which is a lithium-ion battery charging controller, nothing fancy. And of course, we have a flash memory chip for the MCU and the EEPROM for the DMM chip. Overall, the internals are more or less what I had expected. Well, that pretty much concluded this video. For a multifunctional meter well under $100, there isn't too much to complain about. The oscilloscope implementation could be a little better, as you saw it was struggling a bit when trying to view a modulated signal. The multimeter current range has some quirkiness, but it is surprisingly fast in resistance mode. There's nothing fancy about the built-in function generator, but it is definitely useful. Let me know what you think in the comment section below. Anyway, I hope you enjoyed the review and teardown. If you liked the video, please remember to give it a big thumbs up and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.